Okay, so hello everyone. Okay, so my name is Vyacheslav. So my full name is a bit complicated for any non-Russian native, so that's why I usually use like the second part of my name. Usually people know me as Slava. So I am assistant professor at CIMIS, and I am actively working on tropical mirror symmetry, and I decided to kind of make a course summarizing like my works on tropical mirror symmetry in last 5 years, and kind of make it more accessible to students in hopes that maybe some students would be interested in working on this subject. So one thing to mention is that most of my works are in collaboration with another senior faculty at CIMIS, Andrei Losev. And most of kind of results on which I will base my course are kind of in our paper series. So some of them are published, some of them are still on archive. Okay, so now let me kind of do two things. Luis, can you create like WeChat group for like people who are like here in this room? So let me talk a bit about logistics of our course. Okay, so the name of our course is tropical mirror symmetry. And I think it has some official letters and numbers. So it's registered as a course in math department, and its number is 094. So as far as I understand, I actually haven't checked exactly whether there are any holidays on Tuesdays, but modular holidays, there will be 15 lectures in total, maybe minus holidays if any. So it is a pre-credit course. So therefore our lectures will be 2.5 hours with hopefully 2 short breaks. I will try to kind of arrange breaks somewhere near each third of the lecture. So then, starting from lecture 2, so I will assign homeworks. So mostly it will be something like weekly homeworks or close to weekly homeworks as I can. So it starts after lecture 2. So totally there will be 7 homeworks. And all of them will be like equally weighted by 100 points. And the rules for homeworks are the following. So we will have 1 week to solve. So essentially you need to submit your solutions before the beginning of the lecture on 1 week after the homework assignment. Unless I kind of give everyone an extension or kind of you ask me extension due to some unforeseen reasons. Okay, so the submission procedure for homework, so there will be 2 options. So once again, it is official course in Sudan. So there is a course website. So there are two options. So you can use course website if you kind of officially registered for a course, or I will post like homeworks in kind of WeChat group, and you can get homeworks in the WeChat group, and then you can send me an email with your solutions. I will kind of grade it and return to you via email. So once again, kind of if you registered to this course officially, I encourage you to use course website because it is more convenient for me, more convenient for you, and it's kind of much easier to track all homeworks rather than using email. So that is an option only for people who for some reasons didn't register. So we will like kind of copy all. I will copy all materials on the course website in a WeChat. So the homeworks. So then there will be lecture notes that I will update weekly. And this lecture is video recorded, so I will also post a link to video recording. So in case for some reason you missed a lecture, you have like a lot of opportunities to kind of catch up by looking at the lecture notes, by watching video recordings. Okay. Yeah, so then as the very last lecture, so from week 16, which is last lecture of graduate courses, so we will have kind of in class oral exam. So it means that I will give to each of you like a couple of questions. You will have some time to prepare, and then you will like give a brief presentation on the board, like one by one, on these questions. So, questions, preparation, and brief presentation. So I think some of you have taken Andrei Losev's course last semester, so you're kind of familiar with this style, so you can ask your fellow students how it went. Okay, so and final thing is kind of how the grades will be assigned. So the final grade will be assigned in the following way. So there will be 7 homeworks, each weighted by 10%, so all of them equally weighted. And this final exam, so that is homework, and that is final exam, will weight 30%. So that's why I encourage you to kind of do well on the homeworks, so you don't need to worry that much about final exam because it wouldn't affect your grades that much if you perform very well on the homework. Okay, so that is kind of organizational things. Do you have any questions about the structure of the course, like how we will arrange our course? Okay, so if there are no questions, let us do the following thing. So my plan for the rest of the lecture today is to give you kind of introduction. So that will be historical introduction to mirror symmetry. And later, like after this historical introduction, I will kind of also discuss in details 2 topics. So I will talk about surf counting And I will talk about kind of briefly about visualization of mirror symmetry to just give you a general idea of what kind of objects we're going to study, what kind of objects we're going to tropicalize, and what we expect to get. So today is going to be like introduction and roughly overview of the whole course to give you a good idea whether you want to take this course or you want to take some other course. Okay, so now I need to look at my notes, but I don't have time on the dates. Okay, so mirror symmetry. Okay, so the history of mirror symmetry begins in I think 1985 with this kind of famous paper about string complications. I think it was paper. Yeah, I think it was Candelas, Horowitz, Preminger, and Witten. So that is kind of paper with several thousand citations, written by this great physicist, and I think at least two of them, I think Strominger and Witten, would come to string conference that will happen this summer in Shanghai. So I encourage you to kind of come and see some talks by all these great people who made the history of started this mirror symmetry activity. The kind of brief idea of this paper was the following. So in 1985, it was a time when people actively studied string theory. And kind of what people discovered, actually it was superstring theory, that for consistency, string theory requires kind of string theory is only consistent in 10-dimensional spacetime, while we live in 4 dimensions. So we live in 4-dimensional spacetime. So therefore, if we want to kind of use string theory to explain 4-dimensional real world, we need somehow to go from 10-dimensional string theory to 4-dimensional impulse space. And what these four great scientists suggested, they suggested to compactify string theory on 6-dimensional manifold. So in this way, kind of 10-dimensional space will be this 6-dimensional manifold times our 4-dimensional Minkowski space. So the string theory lives on M10, that is x6 times R31. Okay, so there are certain properties of x6 which we need to kind of get a physics that looks similar to physics in the real world. So we want this space to be compact. And for the sake of kind of having physics strictly 4-dimensional, we want it to be small size. So that is kind of easy part. The more complicated part, and I think up to now it's still phenomenologically debatable, whether we want to have any supersymmetry in 4 dimensions. So I think at the time people kind of have bigger phase in four-dimensional supersymmetry. So they kind of assumed that we have certain amount of four-dimensional supersymmetry. So that implied that this X6 should have an additional property that it should have SU3 holonomy. So holonomy for kind of connection in a tangent line. Okay, so this requirement was purely from supersymmetry considerations. And the problem was that it is hard to find manifolds with some prescribed holonomy. So it's kind of easier to find a manifold with even smaller holonomy, like if you take X6 to be six-dimensional torus. So the holonomy will be something very trivial. So holonomy will be some smaller subgroup of SU3. And then similarly, like it's easier to get like SU2 holonomy and the smaller ones. However, for various kind of analogical reasons, people want SU3 holonomy. And then I think a few years after kind of discovering the importance of these six-dimensional spaces, it was Professor Yao who proved Calabi conjecture. And Calabi conjecture was essentially a kind of an equivalent description of this six-dimensional manifold. Calabi conjecture in rough terms. X6 this SU3 holonomy has a nice description in terms of algebraic geometry. So it is scalar variety, okay, complex dimension 3. With vanishing first Chem class. So this kind of proof of Calabi conjecture, it opened up a kind of a way to efficiently construct this six-dimensional manifold with SU3 holonomy by the means of algebraic geometry. So there is a very canonical construction of a manifold with zero Chem class. So kind of, let's say, typical construction. So you take a four-dimensional projective space. So C1 of P4 is 5. So it is not zero. But instead of taking P4 itself, so we take a kind of hypersurface in P4. And that kind of hypersurface, it has certain degree. So degree E hypersurface means that we have a kind of homogeneous polynomial of these 5 variables, which are homogeneous coordinates on P4. So we have homogeneous polynomial of degree E, and our hypersurface is just a kind of vanishing set or vanishing locus for this polynomial. And it turns out that kind of C1 of this HT, so hypersurface is codimension 1, so complex dimension of this HT is 3. So it is one complex equation on kind of in four-dimensional space. So this thing is kind of 5 minus d. So therefore, if I take any degree 5 polynomial and I take a variety that is vanishing locus of this degree 5 polynomial, I will get a three-dimensional Calabi-Yau. So d equals 5, DHT is Calabi-Yau threefold. So these spaces possess three holonomy, okay, they're called Calabi-Yau spaces. And this kind of most simplest construction and most famous example is known as a quintic Calabi-Yau threefold. So quintic refers to this. Okay, it's this 5, but it refers to degree 5 polynomial. So kind of degree 2 polynomials, quadric, cubic, quartic, and quintic for degree 5. And kind of this quintic Calabi-Yau is very famous, and I think up to now is probably the most studied Calabi-Yau threefold. People studied like all properties of it, like in Gromfit invariance and periods and all fancy stuff. And I think in front of the institute you see Calabi-Yau square, name it of the Calabi-Yau varieties, and this kind of yellow shaped thing is supposed to be a real section of this Calabi-Yau quintic threefold. So you see it's kind of very famous. It has its own kind of monument to it, and the square, name it up. Okay. So now that we have kind of a way to construct this Calabi-Yau threefold, so you can kind of generalize this construction. You can look at, say, projective space of higher dimension and take like couple of hyperplanes, and also given some relation on degrees, you can kind of generate different families of Calabi-Yau threefolds. So usually I think these complete intersections in projective spaces, they're often referred to as the toric Calabi-Yau threefold. Okay, so now that we have this kind of object, this complicated object of manifolds with SQ3 holonomy, which is important for getting four-dimensional physics, and we kind of using Calabi-Yau theorem, we can analyze it by means of algebraic geometry. So the simplest invariant of this Calabi-Yau threefold, they are Hodge numbers. So you're probably familiar with cohomology. Or homology, so some kind of Dirac homology, say effects, or some kind of chain homology of X, and kind of Hodge numbers is essentially some kind of refinement of all these cohomologies. So let's say that X is a compact, smooth. So all this kind of homology and cohomology, they are essentially isomorphic. So let me kind of, for concreteness, say that it is refinement of the RAM. So usually the RAM cohomology, it kind of has single label which is n. So kind of omega in n means the degree of omega is n. So omega is n4. So now because all these manifolds, they are complex manifolds, so we can essentially decompose tangent bundle into kind of holomorphic and anti-holomorphic part. So therefore we can kind of label all forms by a pair of labels. So instead of kind of single label m, which is degree now we can separately label like degree in holomorphic and anti-holomorphic values. So for this we kind of has roughly PDV and two DV ones. So and kind of in the RAM theory we have basic numbers. So this became the just dimension of case homology, while in kind of theory of complex varieties we have Hodge numbers. Okay, so they are called, okay, so Betty, B is for Betty, H for Hodge, so they are labeled by now by pair of integer numbers, and they are dimensions of kind of the rank homologies for forms with kind of n holomorphic degree and n anti-holomorphic. Okay, so that are kind of simplest invariants that we can define for complex manifold, and due to some other properties of Calabi-Yau threefold, so Calabi-Yau threefold properties imply that among all these numbers, so this n, they kind of run from 0 to kind of complex degree of x. So normally you would say that, okay, so these numbers. So normally you would say that for Calabi-Yau threefold, you should have like 16 such numbers because n and m run over 4 values. However, it turns out that among 16 Hodge numbers, there are only 2 independent, H11 and H21 are independent. So the rest of the Hodge numbers, they are fixed by some properties, so they're either 0 or 1 for Calabi-Yau threefold. So essentially, the kind of topology of the Calabi-Yau threefolds has these 2 invariants, and in kind of for our so now the interesting fact, which was discovered slightly later by studying this various examples of Calabi-Yau threefolds. So people discovered that often they come in pairs, and like X and another kind of member of the same pair is X check, such that the Hodge numbers for X and X check are interchanging. So it means that H11 for X is H21 for X check, and H21 for X gives H11 for X check. And later, these pairs got its own separate name. They are mirror pairs. And for these mirror pairs, there is this nice property that their Hodge numbers somehow exchanged, H11 exchanged with H21. And not surprisingly, that the first mirror pair was kind of a pair for or mirror brother for this Calabi-Yau quintic. Let me keep Calabi-Yau quintic and describe for you with mirror. So let us kind of specify this degree 5 polynomial to the following one. So we define x psi as a kind of degree 5 hypersurface given by the following equation. So we take like a sum of its power of all coordinates x0 to x5, and then subtract 5 psi and product of all these variables. So that is degree 5 polynomial. So this the corresponding hypersurface is Calabi-Yau threefold, and it's quintic threefold. So here, kind of psi is just some complex number, and kind of for generic psi. So this x psi is smooth. So once again, if you set say psi to 0, so then you immediately see that it is not smooth, but for general psi it is smooth. Okay, and I think this Calabi-Yau threefold has its own name in the literature. I think it's called like Fermat quintic. Okay, so now let us consider an action of some finite group on this Fermat quintic. So this group constructed in the following way. So let us kind of consider Z5 as a multiplicative group for 5 elements. So essentially Z5 is just kind of identity psi square, psi cube, psi 4, and psi is just fifth root of unity. So it's just powers of fifth root of unity. You can multiply them and still get like some fifth root of unity. So it's kind of 5 different fifth roots of unity. Okay, so now using the G5, let us define the following group. So let me take kind of 5 copies of this AK in G5. So kind of 5 elements from this group, and impose the following condition that the product of them equal to 1. So that leaves only 4 of them independent. And then let me also quotient by the following element, by a kind of diagonal element, A and A also in V5. So we say that kind of we identify these 5 elements up to overall up to multiplication each of them by the same root of unity. So therefore, kind of as a group, it is V5 to power 3. So there are only kind of 3 independent copies of V5, but they're kind of packaged in this like 5-dimensional thing with a constraint and the group. So why do we package them into kind of 5-dimensional object? Is because in this formulation there is kind of immediate action of this G on X psi, and some kind of the action is given in the following way. So we take like homogeneous coordinates on P4, and kind of the action. Yeah, okay, let's start with this kind of action on P4. So we take this homogeneous coordinates and multiply them by A0 and A4. So that is a valid action on P4 because we quotient by multiplication over the same element. So therefore this homogeneity in coordinates is still present. So now the important part about this Fermat quintic, that with this additional condition that product of this A's is 1, it preserves, this kind of quintic equation. Let me show it. Z5 capital F. Fermat quintic. So it preserves this polynomial of degree 5, because all this x0 to a power 5, so this group x trivially, because xi to the power 5 is just 1. And here we have product of all coordinates, and we specifically impose that the product of this 5 AKs is just 1. So because it preserves Fermat quantity, so G acts on this hypersurface, so it acts on x psi. However, action has fixed points, and therefore kind of x psi modded by this G action is not smooth. However, it turns out that we can resolve all the singularities. Okay, singularities can be canonically resolved. And we get a kind of variety x psi check, which is kind of x psi over G is with kind of singularities resolved. So because we kind of motion by a finite group, it is still threefold, and it's kind of straightforward to show that it still has vanishing first Chen class. So it is a Calabi-Yau threefold. So it is Calabi-Yau threefold, and resolution of singularities kind of preserve this vanishing Chen class property. Okay, so we have this pair of Calabi-Yau threefold, x psi and x psi check. So now I promised it. Okay, I unfortunately erased it. So I promised it that for a mirror pair, we would have a kind of exchange in a Hodgson. So okay, now we need to give some names, so because it's supposed to be historical thing. So first, this mirror pair was also suggested by Green and Plesser. So Green and Plesser. Yeah. So they didn't quite get it from geometry. So Michael Green is kind of very famous string theoretist. So they got it from string theory. But nevertheless, they kind of showed that x psi and x psi which it resolved form the pair. Okay, so now let us kind of briefly outline how to verify this property that h1 of x psi equals to h1 x psi check. And then similarly, h1 of x psi is h11 of x psi check. So we need to kind of include these Hodge numbers. Okay, so let me start with somewhat simpler one. So let me start with h11. So this h11 kind of describes what is called scalar modeling. So it essentially describes like size of the cycles in our variety. And it turns out, because P5 itself or P4 itself is kind of very easy variety, so H11 of P4 is just 1. So there is one kind of scalar class, which is class of Fubini-Study form. So it turns out that the same holds for hypersurfaces as before. So there is some kind of theorem that claims that for hypersurfaces as before, regardless of degree, this H11 is also 1. So therefore, this computation is kind of very easy. H11 is 1 due to construction of x psi as a hypersurface in a projective space. Okay, so what about H21 of x psi? So H21 of x psi, let me use different numbers with blue. So it corresponds to complex model. And it turns out that this complex moduli, in the case of hypersurface in projective space, they also have a very simple description. Okay, so I don't need this group anymore. Yeah, maybe I'll keep permagnetic inside. Permagnetic. So we have this kind of zero locus of degree 5 equation. However, this permagnetic is not the most general degree 5 equation. So we can kind of take this permagnetic and obtain another quintic if we add, say, some other homogeneous degree 5 term. So we can add something like x naught 4 times x1. So that is also p5 prime is also degree 5 polynomial. And it turns out that all such additions, they describe deformations of permagnetic. And it can be shown that these deformations, they essentially describe complex models. So therefore, to count H21, we need to do the following thing. So we need to count kind of number of deformations. So we can deform by any homogeneous monomial. So number of degree 5 monomials in 5 variables. Yeah, and then we can also, so this x0 to x4, they are homogeneous coordinates on P4, and P4 has kind of isometry group, which is SL to SL5C. So you're probably familiar with the isometry group of P1, which is SL2C. And then kind of in a similar way, P4 has higher isometry group SL5C. So it means that if I am given a kind of degree 5 polynomial, I can still do some linear change of variables in P4, like linear change of coordinates, and get another degree 5 polynomial, but it will describe the same hypersurface up to this change of variables. So that's why here we need to subtract dimension of SL5C. And all these polynomials, they are homogeneous, so we are looking at a zero locus. So we are solving the equation with P5 equal to 0, and this equation is kind of false up to overall multiplication by non-zero constant. So we need to subtract 1, which is kind of overall multiplication of this polynomial by non-zero complex number. By element of P5. Okay, so now we need to, okay, so we already computed this number 1, which is number of overall multiplication. So dimension of SL5C, so 5 times 5 is 25, and one determinant condition is 1. So this thing is 24. So here, degree 5, number of degree 5 monomials in 5 variables So it is 5 plus 5 minus 1, choose 5, which is 9, choose 5, and if I'm not mistaken, it's 126. So therefore, what we get 126 minus this 24 minus 1, so it's 126 minus 25. So that gives us 101 for H21. So we see that this kind of huge difference, H11 is like as small as it can be, just 1, and H21 is rather huge, like 101. Okay, so we did computation for these Hodge numbers for ordinary quintic. Yeah, and let me kind of outline computation for a dual quintic. So this computation is more complicated. So let me start with kind of H21. So we identified H21 with kind of deformations of an equation that defines this hypersurface. So now, unfortunately, I erased the action of a group, but recall that the action of a group was kind of multiplicative action. So we multiplied each x by the corresponding a, and we observed that Fermat quintic was invariant under this action. However, if I start deforming Fermat quintic by okay, I have different color. Let's make it. So if I start deforming Fermat quintic by monomials, by homogeneous monomials of some other form, so they generally will not be invariant unless they are proportional to monomials that are in Fermat quintic. So therefore, G action, it kind of eliminates all deformation except the single one, which is deformation by itself. And therefore this number equal to 1. So because of the quotient by G, we essentially eliminated all deformations, and only psi deformation remains. Okay, so that was kind of easy part, and H11 of x psi is a more complicated computation. So what we have? So we have 1 because it kind of originated from hypersurface. So it still carries this 1, which is size of P4 or size of hypersurface P4. So as I mentioned here, this quotient is not smooth. So there are like fixed points, and more general, there are like some fixed submanifolds of this action. And kind of for a fixed point, this resolution procedure is essentially a blow up at a point. And blow up at a point, it kind of introduces an additional P1 cycles. So we will hopefully see this in a bit more details when we talk about toric variety. But here will be some kind of an additional 40 and additional 60, which is kind of, one of them is blow up points, and other of them is blow up of some lines that are kind of fixed points of this G action. So essentially, you can kind of identify these numbers 40 and 60 by counting fixed blocks. But then you need a bit more complicated procedure to kind of deal with these deformations and resolution of singularities to kind of show that it is indeed 40 and 60 new cycles, and that kind of raises this number H11 from 1 to exactly 101, which kind of matches with H21 of x psi that we computed by counting coefficients. So that was was kind of first example of mirror pair, and we kind of explicitly constructed xpsi and xpsi check, and even verified this prediction, this main property of a mirror pair, that the Hodge numbers are exchanged. I think now it's a good time to make, let's make 5-minute break till 10:51, and then we will proceed to the second part of the launch. I'll be back. Okay, I think it's time to continue. Okay, so in the first part of today's lecture, we learned about first pair of mirror pair. It's called the symbols. And once again, so people continue to study this Calabi-Yau threefold, and I think a few years later, I think Candelas and collaborators Candelas, De La Osta, and Green and Parks. So later they kind of by looking at these mirror pairs and by using some once again string theory methods, so they managed to kind of provide an answer to very classical problem in algebraic geometry. Solve it. Classical problem. In algebraic geometry known as the curve count. So we have this complicated three-dimensional complex variety, and inside this three-dimensional complex variety, you can say have like some lines, and there is a very classical problem like how many independent lines are there on this variety, and for Fermat-Quintic, the answers for lines and the quadrics were known for quite some time. So the answer for lines is 2875. So that was kind of 19th century result. And kind of a bit more recent result for number of conics is 69, 250 was kind of computed by Katz in 1986. So that kind of around the time when Candelas and collaborators studied this thing. So that's why like two numbers. So that is kind of number of lines, and that's kind of number of quadrics inside this kind of Fermat-Quintic variety. So these numbers are quite huge, so not surprisingly that for counting quadrics it took quite some time and this modern result. And at the time of that paper by Candelas, the number of cubics, that was quadrics, degree 2, degree 1, degree 2, and for degree 3, at the time the number was unknown. And Candelas and collaborators used this kind of idea that the Calabi-Yaus came in pairs. So they managed to connect a kind of number of degree d curve in this x psi with some kind of periods of x psi check. So both x psi and x psi check, they are three-dimensional Calabi-Yaus, and kind of that implies that both of them have non-degenerate holomorphic 3-0 form, and it is unique, and we can kind of integrate this 3-0 form over some 3 cycles, and we will get some numbers, or if we look at the family of calabials, we will get like some functions of deformation parameters. So using this idea and using some kind of motivation from string theory, they managed to connect number of curves and the periods, and furthermore, they managed to kind of extract from this relation like this numbers and d, and they verified that these two numbers match. So this is kind of non-trivial statement that the 6-digit number matches with some other random number period. And furthermore, they managed to compute degree 3 number, which is I don't remember it by heart, 317, 206, 37. So that is kind of number of the size of telephone number, so 9 digits. So they made a prediction for number of cubics. So that was prediction by Candelas, and I think later, like several years later, in 1990, so this thing was verified. So now prediction from kind of mathematical physics was verified in algebraic geometry. So algebraic geometry verified, and that was kind of first and very famous example when people used string theory and mathematical physics to get some very new answers to a classical algebraic geometry problem, like counting some degree d curves in certain variety is a very classical problem, and for Fermat kinetic, the first counting for cubics were done using kind of string theory, mathematical physics methods, and only later it was verified by algebraic. So this kind of computation, it sort of showed to mathematicians that all these strange string theory methods and all the physics might be actually useful, if not kind of proving something, but kind of generated explicit numbers which then can be verified by kind of standard methods of algebraic geometry. So this kind of success of this result by Candelas and successful connection to algebraic geometry, it kind of created whole new field of kind of study. So result by Candelas kind of open a new field of curve counting, general enumerative invariance. New fields of study using mirror pairs and physics theory, math physics. Okay, so we will talk in a bit in more details about the kind of other enumerative invariants which generalize curve counting. But let me kind of briefly outline the kind of rest of the story between, I think it's kind of 1990s and kind of tropical mirror symmetry at the present day. Okay, so that was result in 1990s, and people kind of continue to study these mirror pairs and continue to generate various conjectures. And all this kind of lasted till 1996, where people got first proof of mirror symmetry. So proof, in a sense, that that they managed to kind of explain how the curve counting on one side and periods on the other side, how they are related and why they are related. And these first two proofs are kind of done independently by two groups of people, so it is given time. And probably more familiar to you is Liang, Yu, and Yao. So that is a group of chemists, mathematicians, and mathematical physicists. I think I already mentioned Professor Yao, who was like proved this Calabi conjecture, and kind of Liang is the Bond Liang, who is vice director of our institute. So we see our institute has kind of long tradition of doing great things for mirror symmetry. So and one of first proofs of mirror symmetry was kind of done by this group Liang, Yu, and Yao in a series of several papers. I think it's kind of called mirror principle papers. I think it's series of 6 papers on archive. But once again, this proof was kind of purely mathematical proof. So while the origin of mirror symmetry was okay, so that was kind of first proof of mirror symmetry in kind of context of related Calabi outcomes. So I think around that time, I think in 1994, so Kontsevich, in collaboration with Manev, so they managed also to use kind of mathematical physics string theory methods to solve yet another classical problem in curve counting. So they performed curve counting, but not in Calabi-Yau threefold as we discussed here, but in projective space. And in P2. So P2 is not a Calabi-Yau, so the Chen class of P2 is 3, so it is positive. So it is Fano variety, but nevertheless, they managed to perform curve counting, and furthermore, this curve counting was related to some other object from mathematical physics, W dV equation. So it stands for Newton, digraph, Verlinde. And that was also some result that physicists discovered by studying topological theories, and Kontsevich and Manin managed to use this result to write down some recursive formula for curve counting at P2. So therefore, in that time, people kind of discovered that mathematical physics methods, they are not only good for curve counting in Calabi-Yau threefolds, but can be applied to curve counting in a different varieties. So that kind of raises a question whether there is some kind of mirror symmetry for non-Calabi-Yau, say for PN. Just for projective space. So that would be nice because projective spaces are kind of much easier to study than Calabi-Yau threefolds, and that maybe understanding mirror symmetry in this simpler setting would be helpful to understand it in historical setting of Calabi-Yau threefolds. And it turns out that the answer is yes to this question. Is there mirror symmetry? Indeed, there is a mirror symmetry. However, this mirror symmetry is kind of okay. When it was originally discovered, it was discovered as not geometric relation. So the relation was the following: so Gromov fit and invariance. So that are kind of generalization of curve counting. You can for a moment think that it's curve counting on a projective space or more generally tonic variety X. They kind of mirror dual to Landau-Ginzburg model on C star on kind of algebraic torus of the same dimension as the toric space X. So for Pn it's just algebraic torus to dimension n with a certain mirror superpotential. Let me kind of schematically write it like this. So with certain exponential superpotential. And it turns out that in this Landau-Ginzburg model on C star to the power n, so there is kind of analog to a period formula. Like for Calabi-Yau, recall that the period formula was kind of integrating 3-0 form over some 3 cycle. So that was Calabi-Yau threefold, and in kind of Landau-Ginzburg model, you have a very similar formula in the following sense. So C star to the power n is also non-compact Calabi-Yau. So C star to the power n also has holomorphic top form. So in this coordinate, it's just a product of divides. So we take this holomorphic top form. And now what we need to do, we need to take like product of some partial derivatives of the W in denominator. So W has poles somewhere, and here we need to take like a certain residue integral over some contour gamma. And this formula is kind of an analog of period integral for Calabi-Yau, but formulated in Landau-Ginzburg model. So that was kind of an additional reason why we still call this correspondence between Gromov-Its invariance on projective spaces and something which doesn't quite look geometrically with Landau-Ginzburg models, a mirror duality. So it turns out that in some special cases, so we can further kind of upgrade this Landau-Ginzburg model to kind of certain Calabi-Yau variety and turn this formula into honest period integral. But for the sake of this course, we are not going to discuss this kind of upgrade of Landau-Ginzburg model side to kind of honest period. So our kind of correspondence will stop at a certain residue formulas that are period-like formulas. Okay, and given this kind of correspondence, the main question is kind of how to get this mirror superpotential W given toric variety X. And this question was beautifully answered by kind of famous work of Florian and Waffa. And once again, Kummer and Waffa also coming to things. So you see all these big names. They are still active and still coming to a conference. I think it's 2000. So they used some supersymmetric gauge theories. Or I think they go under the name gauge linear sigma models, GLSM. So they use GLSM construction for toric variety X, and then they kind of performed QFT duality. and turned it into Landau-Ginzburg model with mirror superpotential. So in their kind of construction, it was a bit indirect because they need to do this extra step in kind of describing invariance on X or nonlinear sigma model on X in terms of gauge linear sigma model. So there might be some potential issues with this construction, but nevertheless they got superpotential, and given a superpotential, you can just compute these periods and verify whether they match with some curve counting that is classical in some simple cases like P2. So the answer for curve counting for a small degree was also known for a long time.
How does this degree of curve enter this integral?
We will get to that in kind of in the later part of the course. So
I cannot see there is a parameter d inside this.
yeah, so here, like if you do a curve counting, there will be yes curves of degree d, but usually what you do, you kind of organize the number of curves of different degrees into some kind of polynomial of a new variable q. And here, this mirror superpotential, it also has some q dependence. So therefore, this right-hand side is some function of q, and the left-hand side became function of q if you treat this number of curves as a coefficients in some kind of q expansion. And in the case of toric variety, you can show that both left-hand side and right-hand side are just polynomials in q. And that's kind of what makes this mirror symmetry for toric spaces simpler than Calabi-Yau, because in Calabi-Yau case, both the series are usually infinite series in Q, and therefore you need to be more kind of careful in stating this relation. Okay, so that was resolved by Hori-Waffa, so it was proof, but not quite proof that was satisfying, because they used this kind of intermediate step of gauge linear sigma model. However, I think sometime later, okay, oh, I think it was, 2005, it was Frenkel and Blosset. So they provided a kind of more direct proof. So they used a kind of realization of nonlinear sigma model, which is kind of physical description of Gromov-Fit invariance. So they realized it as kind of free sigma model plus some additional holomorphic operators. And then they managed to kind of perform T-duality in this theory, and also arrive into Landau-Ginzburg model with mirror superpotential, and their mirror superpotential was identical to mirror superpotential computed by Hori and Waffa. So that was kind of upgrade on the proof using physical methods, where we eliminated like one intermediate step, like this gauge linear sigma model construction. So they managed to perform this mirror duality using kind of more straightforward nonlinear sigma model description of Gromov-Fit invariance. Okay, so that was kind of generalization of a mirror symmetry to include toric varieties, and most of our course will be focused on this setup for mirror symmetry. So we will kind of describe how to get from Gromov-Fit invariance on toric variety to certain residue formulas in Landau-Ginzburg. So in this course, we are not going to discuss mirror symmetry for Calabi-Yau threefold or even for Calabi-Yaus of different dimensions. Okay, so now let me say a few words how we got from these results by Khorivaffa, Frenkel, and Losev to kind of tropical geometry. So I think going back to the mirror for Calabi-Yau, so in 1996, Sperminger, Yau, and Zaslav they formulated an interesting conjecture, which is known as SYV conjecture, as a way to construct kind of mirror pairs, so mirror pairs by T-duality in T3 vibration. So their idea was the following, that the certain classes of Calabi-Yau threefold can be constructed as a vibration. So we look at three-dimensional plane. Okay, I can draw three-dimensional plane, but I can draw it demo version, two-dimensional plane. And here we have kind of three-dimensional torus, fibered on over each point. So if this vibration is not degenerate, then we get like a non-compact Calabi-Yau threefold star cube, which is RC. However, you can compactify it by kind of adding some kind of graph in this graph homogeneously simplicial complex in this R3. Let me use a different color. So kind of add some kind of graph in R3 such that vibration degenerates, so it's degenerate locus of the vibration. And that kind of way of construct certain Calabi-Yau threefolds. So and the data is this degenerate locus where vibration degenerates. So then they say the following thing. So this T3 is essentially S1 cross S1 cross S1. So it's 3/4 of a circle. So then what we can do, we can perform T-duality on one of the circles. And then we will get some kind of dual T3. And then we can consider a vibration of dual T3 with kind of the same degenerate locus. And that presumably, so T3 check vibration over R3 should give us kind of mirror Calabi-Yau. So T3 vibration over R3 gives Calabi-Yau, and vibration of a dual torus gives a mirror Calabi-Yau. So this conjecture, it kind of opened up a field of study of sort of toric vibrations that degenerates over some lines or over some simplicial complexity. And it turns out that this picture of torus degeneration over some line kind of naturally emerged in toric geometry. So it's very naturally okay. So it is kind of present in toric geometry, but kind of in toric geometry you open a lot to torus to degenerate at infinity and not at some finite graph, and kind of torus vibration with degenerations over graph. So that was kind of naturally appear in vertical geometry. And I think around 2000, early 2000s, it was once by Kontsevich. kind of suggested that maybe appearance of tropical geometry is not accidental in this SYZ conjecture, but this kind of signature of some more important phenomena, and he conjectured a possibility of curve counting using tropical geometry. So that was usually just kind of some remark by Maxim Kontsevich, and kind of this remark was further investigated by Grigory Mikhalkin. So I think it was 2008. Let me check it. No, sorry, my bad. It was earlier. It was 2003. Grigory Mikhalkin. So he actually took this idea by Kontsevich seriously. So he performed curve counting in this very famous example by Kontsevich in P2 by tropical geometry method. And to his surprise, he discovered that this number of degree D curve that we will discuss in kind of maybe in 10 minutes, the number of computing counting tropical curve, they exactly match the numbers computed by means of algebraic geometry over C. And that was kind of great result, because that provided a proof of a concept that that it is possible to solve classical algebraic geometry questions by using much simpler tropical counting. So algebraic geometry questions have exact answers in tropical geometry. And we will see, hopefully by the end of this lecture, that kind of tropicalization or tropical geometry is essentially a certain limit. So some people would say even classical limit of complex numbers, and then usually going to some simplification limit. Often you get like some properties are preserved, and then some properties are just destroyed because you simplify your problem. And it turns out that the curve counting and a more general Gromov-Witten invariance, they actually invariant undertaken this limit, and this kind of great result was kind of known nowadays as Mikhalkin's correspondence principle. Is that enumerative problems in complex geometry allow for tropicalization, and tropical counting gives the same answer as a complex geometry counting. And that kind of this result by Mikhalkin was a starting point of yet another research area. So since 2003, so people start doing kind of tropical comparative geometry, and usually kind of an interesting piece and kind of natural piece of enumerative geometry is thinking about whether this tropical counting, whether it is mirror dual, and kind of asking questions about performing mirror duality to this tropical counting, and kind of see what kind of results we would get. And that kind of area where I am working in collaboration with Andrei Losев, and most of our course will be focused on kind of carefully defining what is tropical counting, and I will describe what is the mirror symmetry in this tropical setting, and by the end of the course we will carefully go step by step towards proof of mirror symmetry in a tropical setting. Okay, so let me see how I do this time. 11:27, so I think I still have. Yeah, let me spend a bit more time before break on. Yeah, on starting. Yes.
Is the SYZ conjugation solved for Calabi-Yau twofold?
I think for Calabi-Yau twofold, the story is that I think there is only one Calabi-Yau twofold, which is K3 surface. So the conjecture is kind of very poor, I think, for Calabi-Yau twofolds, at least if you require it to be compact and smooth. So I don't know whether there is a version for something like non-compact Calabi-Yau twofolds. That's I don't know. So it's a good question, and I don't know the complete answer. For smooth Calabi-Yau, it just check. Okay, so now let me go to next topic today is to give you a bit more details about curve counting, and to be more precisely about curve counting in P2, because that will be kind of geometric problem that we will tropicalize in the first third of our course. So curve counting. In P2, and I also will kind of mention some results that some kind of generalization to a toric variety. Okay, so let us start with the problem formulation. So the kind of classical algebraic geometry question. Now many degree E rational curves are through 3D minus 1 points in P2. So that is our question, and the answer would be integer number n, capital N subscript E for different degrees. Let us start with kind of classical result from algebraic geometry. So algebraic geometry can predict these numbers and D for small enough D with kind of some increase in sophistication. Okay, so the first one is D equals 1. So 3D minus 1 is 2. So we have degree 1 curve. So degree 1 curve, degree 1 rational curve is just line. So it's a variety which is zero locus of homogeneous equation of degree 1. X2 equals 0. So all these x's are homogeneous coordinates in P2. So that is kind of our line. So degree 1 line, and this degree 1 line is parameterized by 3 complex numbers. But once again, because we're in projective space, we can kind of rescale our coordinates and rescale our numbers. So modulo C star rescaling. So that leaves us with kind of, okay, so at least one of the numbers should be non-zero. So all three of them can be zero. So three numbers with a non-zero product modded by overall multiplication by non-vanishing complex number. So therefore we have like two parameters for this line, and now the condition that line passes through 2 points means that, let's call this polynomial T1, that T1 that depends on A as a parameters and depends on X. So we substituted the value of the point x1, it vanishes, and the same polynomial for the same A with x2 substituted vanishes. So that gives us kind of two linear equations on A, and these are two linear homogeneous equations. So that gives us unique solution up to overall rescaling. So it will be unique line in T2. So therefore we conclude that N1 just equal to 1. So here we kind of went through careful argument of very simple statement familiar to many of you, that if I give 2 points on a plane, there is a single line passing through these 2 points. And here is just some kind of P2 generalization of this statement. There is a single line passing through 2 points. Okay, so let's go to G equals 2. So G equals 2, degree 2. So they are quadrics. Degree 2 quadrics. And 3D minus 1 is 5. So we are looking to count number of quadrics passing through 5 points. So quadrics, once again, quadric Q is a zero locus of quadratic equation. So it's not square plus dot dot. So there will be total six coefficients for homogeneous polynomials of degree 2. So I think there is kind of one formula that will be recurring formula. I write it like this. So kind of number of polynomials of degree 2, polynomials with k coefficients is, I think, k plus t minus 1. Choose t. And so once again, here we can count that this number is 6, and all these a's, once again, they are up to is star scaling. So that leaves 5 of them independent. And then once again, equation that this quadric that depends on A passes through 5 points gives us alpha, these coordinates. It gives us 5 linear equations. So linear equations on this variable same. So this quadric is quadratic only in x, but when we evaluate it at some fixed point, so it gives us linear equations on A. 5 linear equations on A gives us unique solution. Unique quadric, so that allows us to compute that N2 is also 1. Okay, very good. So would we be kind of engineers? We would say that N1 is 1 and 2 is 1. Okay, probably N3 is also 1. Like what else can we do? And it turns out that N3 is when things start getting interesting. Okay, so 2 equals 3. So degree 3 curves are cubic. And okay, cubics and quadrics start with the same. Let me call it cubics. Okay, and once again, here we will have some coefficients. So we have like a cubical polynomial, and once again, using this formula, that gives us 3 plus 3 minus 1, choose 3. So it's 5, choose 3. I think that gives us 10 coefficients. So coefficients we not to A9. And once again, modular things are rescaling. So 3D minus 1 is this equation is 8. And now, if we kind of naively try to do the same procedure, to write down like eight linear equations, we would immediately run into problem that we have like after scaling 9 coefficients, 8 equations. So naively, we would have infinitely many solutions. However, this answer is wrong, and it's wrong for the following reason. So the curves of degree 1 and degree 0, so topologically, so degree 1, degree 0 curves, so complex curve is some kind of Riemann surface, and Riemann surface has topological invariant genus. So genus of this curve where 0, so topologically these curves are just spheres. However, I think in the course of algebraic geometry, there is this kind of very classical result. The degree 3 curve in P2 generally has genus 1. And genus 1 curve means that it's not rational curve. So here rational means genus 0. And in this classical problem, we are asked to count rational curves and not genus 1 curves. So there are two ways of kind of modifying our count. So one modification would be to say, okay, maybe the correct counting should be counting like genus 1 curves instead of rational curves. So that gives us modification of our numbers. So our number D, we say that it was actually double index and 0D, where 0 stands for genus. So this 0 is G equals 0. And we can modify this number to N13. So counting genus 1 curve of degree 3. However, if you modify this thing, so then kind of general curve is genus 1, and to fix this 9 coefficients, we need 9 points. So N13 kind of number genus 1 curve degree 3 passing or 9 points. So if you count this number, it is well-defined number, so it's 9 equations, 9 coefficients, but unfortunately these equations are still linear equations. So therefore, yes, we kind of modified our problem, but we modified it in a very boring way that we still continue getting number 1. And that kind of holds for higher degrees, like a curve of degree D. So kind of there is some theorem from algebraic geometry. Is the genus of the curve of degree D is D minus 1, D minus 2 over 2. And generally, if you look at the number of curves of genus G, which is kind of genus of a generic degree D curve, passing through, I think it's 3D minus 1 plus G points. So then all these numbers will be just 1. So they will be the same simple numbers that we get for degree 1 and degree 2. And the proof of this statement is very simple, because we will have exactly 3D minus 1 plus g coefficients for this curve when we mode by C star. And so that is kind of easy to be verified using this formula, and we will have linear equations for these coefficients, and linear equations in a general setting would have a unique solution. Okay, so that's why we need some other modification that is interesting modification, which is kind of alternative is to count the generate curves. So what kind of degeneration we are looking at? So if I schematically draw a topology for G+1 curve, it is some kind of torus. But you can imagine kind of shrinking. You can imagine some kind of shrinking this yellow cycle of a torus into a point. And then this thing is kind of topologically looks like some kind of sphere with 2 points touching each other. So that is this kind of degenerate torus, and that is a sphere where we kind of glue 2 points on the surface of a sphere. So therefore, in this situation, like this additional point that we need to fix coefficients, it kind of roughly emerges as a degeneration point. So we still have like cubical curve passing through 9 points, but it's kind of 8 real points and 1 point where the curve degenerates. So that's kind of how we manage to fix 9 coefficients using only 8 points. So here we have 8 points plus 1 degeneration point to fix. So we will have like 9 equations. So there will be like 8 linear equations for passing through 8 points, and 1 additional equation for existence of this degeneration to fix 9 coefficients in this cubical polynomial. Okay, so now the interesting part is what kind of the equation we get for existence of degeneration point. Let me finish this equals 3 case, and then we will. Okay, so now the kind of question how to describe degeneration. It turns out, so at least I don't know the kind of elementary explanation myself. So kind of for this kind of homogeneous polynomials, you can define some kind of generalization of discriminant, like for quadratic polynomial, we have this thing which is discriminant that let's remember quadratic polynomial something like ax squared plus by squared plus c y squared. So there is kind of an object which is discriminant, which is b squared minus 4ac, and when when discriminant vanishes, so here instead of having kind of 2 roots, okay, let me just do this in homogeneous form. So normally quadratic polynomial has 2 distinct roots, but in this special situation when discriminant vanishes, we have like 2 roots coincide. And that is kind of some special situation for a quadratic polynomial. So it turns out that emergence of a degeneration point for this cubical curve is also related to some kind of analog of this discriminant, but for kind of cubical polynomial of with three variables. So there is kind of discriminant for this cubical polynomial, and it turns out that this discriminant is actually degree 12 polynomial in this kind of degree 12 homogeneous polynomial in this 10 coefficient. And therefore, here we have 8 linear equations. And the generation point will be an equation that is degree 12 polynomial of these coefficients vanish. And by kind of Biot theorem, so over complex numbers, which is algebraically closed field, so generally this condition of degree 12 polynomial vanishing will give us 12 solutions. And therefore we conclude, after this long considerations, maybe I can write it here, that N3, more precisely N03 in our terminology, like genus 0 curve of degree 3, passing through 8 points, is 12. So this 12 is kind of beginning of a more complicated sequence of numbers. So this 12 was kind of known in a classical algebraic geometry. However, next number for d equals 4 and 0, 4, which is 620, was not known and was only computed using Kontsevich Manin recursion in 1990. So that looked like a relatively simple problem in algebraic geometry. Okay, so for d equals 3, okay, we need to analyze some kind of degeneracy, some discriminant condition. But for d equals 4, so if you look at that kind of genus formula, so it's 3 times 2 over 2. So generic genus for degree 4 curve is 3. So that's why kind of generic curve of degree 3 looks like this. And to count rational curve, we need to kind of do a very complicated multiple degenerations into something like so we need to degenerate like these 3 holes into some kind of sphere kissing at kind of three pairs of points. So this is some kind of sphere. And identify. So kind of studying this problem by means of algebraic geometry seems to be horribly complicated. However, by using kind of some ideas from mirror symmetry and ideas inspired by quantum field theory, so Kontsevich and Manin managed to get a recursion formula. Let me just write it here. That MD given by a following thing. So you perform a summation over D1 and D2, so both of them are positive. And it kind of works in the following way. So it's ND1 and D2, and here some complicated expression with binomial coefficients. Okay, so let me just the final part of this part of lecture. Let me just write this formula. So it's kind of not that horrible, but still quite complicated. TV minus 4, TV1 minus 2, minus TV1 cube T2, D minus 4, and TV1 minus 1. So that is kind of some of the great result in numerical geometry. Once again, inspired by mirror symmetry physics and string theory. That is recursion formula that allows us to take like this n1 and n2, which are very simple and we know them, and plug in into this recursion formula and generate 3 and 4 and higher ones. I think that's the point where we stop the second half of the lecture. Let us take 7-minute break, and then we will talk a bit more like how to get this formula and some kind of how to generalize. Okay, so we meet at 12.
本素使用，就它那个12次的方程，
对，它是怎么转？
还有8个1次的方程，就是它那个 projective 非常它那个相交数，就是曲线相交数，就是把这些 degree 乘起来就好。 就是比如说一个2次的方程，定一个2次矩形和一个3次矩形，交出来焦点数就是6个。
这个跟这个有关系。
所以它有一个12次的，就是这个 discriminant 这个是一个什么？就是它说三 cubic curve， 它的 discriminant 是12次。
哦 ，OK，
12次让12次要等于0，它描述了这个 degenerate。然后所以12次等于0，还有8个1次的方程，一个8个1次方程要过8个给定的那个点嘛。所以简单把这个12乘上1就可以了，12乘1乘起来就是12。因为它的相当就是把这个位乘起来。对，就是 intersection， 它这个要满足这9个条件，一次的就是一个12的，就把这个乘起来。是这12它直接给的，接下来2次方程它会给是，
那对于高维的，
所以高维的没法这么算，应该是
高维没法这么算。
高维它就是这个还是。
就是要从头推导一下，他们这个对的，对，
那就不理是一个特别的模型，
就是把它用它来推导出那个 A 模的 B 模的，从什么是你手法？
不是，比如说那个是哪个是？比如说
A 就方式。
Okay, well, so last part of our lecture. So let me make a bit kind of few steps back. So to kind of get to this formula, we need to prepare some things and to give some kind of definitions to explain some ideas. So as we said, like so we discussed these numbers n, g, t. So for genus G, degree E, so P2, passing through, regime x1 plus G points. So around the same time when kind of Kontsevich-Manik proposed their formula, recursion formula for ND, they also developed some kind of formalism for expressing these numbers as some kind of moduli space integrals. So here we look at kind of moduli space of genus G curve is a certain number of marked points. Genus G curves with certain number of marked points in P2 of degree D So they introduced this moduli spaces. We have this moduli space. And to be more precise, moduli space is maps from genus G surface to our P2 and maps of degree D. And we have some number of marked points. It's called maps from genus G curve with n marked points to P2 of degree D. So there is some moduli of these maps, and we kind of organize this moduli into moduli space. So generally this space is non-compact, it has like different strata, but we kind of properly compactify, we add some additional strata, so we do some kind of Savage-Mannion completion of this moduli space. And then these numbers can be obtained as an integral of this moduli space of the following object. So we take product alpha from 1 to the number of points n, so n, 3d minus 1 plus g, and then here we apply a certain evaluation map. So apply it to kind of delta functions on points p alpha. So delta of p alpha is kind of Poincare dual form kind of chain which is point p alpha. So point p alpha has a kind of top form as its Poincare dual. And in kind of physics literature, this delta often called like delta form at a point. So then this kind of evaluation map, they kind of map these moduli spaces to P2, and this map is kind of works in the following way. So we have a curve, and then we have d1 to the end, like n point on this curve. Sorry, not even curve, we have this map phi, which maps sigma gm to P2. So we say that it's moduli space of maps. So that is one of the maps, and these are positions of n points. And what we do, we kind of evaluate the image of this map at the point alpha. So this kind of maps this moduli space into P2, and that's why we can pull back differential forms on P2 to get forms on the moduli space, and then kind of Kontsevich-Mannion kind of show it that indeed we can integrate these forms, and these integrals, they kind of equal to a known numbers, and further they satisfy the same properties as expected from MGD. So that's why through our like in our course, we will mostly use this kind of Kontsevich-Mannion definition for intersection numbers, like definition in terms of moduli space integral, and that would be kind of our main formula that will allow us to go from kind of counting of tropical curves to some higher topological quantum mechanics. So apparently here in this formula we can replace Poincare dual for a point p alpha to just arbitrary differential forms omega alpha from our P2, and furthermore we can actually replace P2 by arbitrary toric variety, by arbitrary variety, not even necessary toric, and the corresponding integrals will give us what is called Kropotkin invariance. So, and usually denoted in a fluid way. So we have some collection of forms, omega 1 to omega n. We have like the square brackets, or rhombic brackets. So here we denote on which space we are looking at, and here we carry additional information about genus of our curve and degree of our curve. So degree for general projective variety might have like multiple components. So it's only for projective space degree is just single integer number, but in general it is an integer vector. So these are kind of labels, classes in second positive homology. And here we basically have an integral of the very same, of the generalization of this moduli space mgn of x of degree beta, suitably completed by Kontsevich and Panin. And here we have the very same product of pullback of evaluation maps, and we just apply them to this form forming alpha and take product over this. So that is kind of how we generalize this curve counting. So we first turned curve counting problem into some kind of integral of a moduli space, and then we noticed that this integral kind of allows for immediate generalization, that P and P2 is not important. All these moduli spaces, evaluation maps, they are well defined for any variety X, actually for any probably any symplectic variety X. And furthermore, like in the integrand, we can replace kind of delta functions at the points to kind of arbitrary forms omega. And if you want geometric interpretation, we can just take omega alpha to be some delta functions on cycle C alpha, and then this Gromov-Fit invariant would have geometric interpretation of genus G degree beta curves in X passing through some collection of segments. Geometric interpretation of alpha delta T alpha, and then this number beta number of degree beta genus G in X passing through cycles C1. So that is kind of generalization of this geometric, classical algebraic geometry question, and we kind of got it from first expressing the answer through the integral, and then kind of modifying integral and integrate. Okay, so that are Gromov-Fit invariants that I mentioned in kind of third part of the lecture. That was natural development of this curve counting question, was a question about computing Gromov-Fit invariants for X. So that Gromov-Fit invariants, they have some nice properties, and I want to list some of them. Okay, so properties. This property will be important for some of the statements that I'm going to. So first of all, having kind of integral of some product of differential forms. So we understand that integral is non-zero. If and only if we have like the dimension of the cycle of which we integrate. So here cycle is just the full space. If dimension of moduli space kind of mentions the total degree of these differential forms, we try to integrate. So evaluation map reverse the degree. So here, like the product of pullback with respect to evaluation maps of omega alpha. So degree of the differential forms on MGN x beta is the same as sum of the degrees of omega alpha understood as degrees in X. So therefore, there is an interesting question of what is the dimension of this model.
One question here. So this number NGD, we expect it to be independent of points P alpha.
Yes, yes.
So if we exchange P1 with P2, sometime this differential form will differ by sign, right?
No, because all these forms, they're even forms. We are on a complex variety. So as long as we are X is a complex variety, or even better toric variety, so all kind of cohomologies. So this kind of integral, it depends only on cohomology classes of this omega. And if X is toric, then all cohomology classes are even. And I think in kind of most situations that we are going to study, all these classes are even. But in more general, say symplectic setting, you can imagine having like omega of kind of odd degree, and then there might be some subtleties. But we are not going to discuss the subtleties in our course. So in our course, like all these delta functions on kind of complex cycles will be even dimensional, and the order wouldn't matter. Thank you for good observation. Okay, so what is the dimension of this modular space? Or sometimes people call it virtual dimension, because sometimes this modular space is not a space. But for now, let us omit this issue. So G and X beta. So for dimension formula, we have three contributions. So one contribution is a degree dependence. So as we say it, like beta is just kind of homology class of our curve. So beta homology class of our curve in second homologies. So we just integrate this two form, which is first chain class of X over this cycle beta. We get some number, and it will be actually integer number. So then there will be Venus dependent. So we need to take complex dimension of X, subtract 3, and I think write 1 minus G. And the final contribution is kind of universal contribution, which is just plus n, where n is the number of arc points. So here we are looking at a complex dimension. So for real dimension, you need to multiply it. Let us formula for dimension, and from this formula we can make several observations. That kind of explain different types of enumerative problem. So let us first look at degree dependence. So P2 is an example of what is called Fano variety. Usually, I think one of the equivalent functions is in the first chain class is positive, and therefore in this situation integral of beta P1 of X will be some kind of will grow with beta. So it means that if I have curves of higher and higher degree, they will have like bigger and bigger modular space. So therefore, to kind of count the number of curves of high degree in kind of Fano variety case, we need to add more and more cycles to saturate the kind of degree of differential form to match with the dimension of this space. So the interesting situation is this kind of Calabi-Yau case, which, as we said at the very beginning of my lecture today, is that Calabi-Yau by kind of Calabi-Yau theorem is kind of complex variety with complex Kähler variety with vanishing first Chern class. So in this situation, if C1 is 0, so dimension is independent on beta. So it means that the curves of a different degree, they kind of contribute to the fixed selection of cycles. So we choose some cycles to saturate this dimension of a moduli space, and then if we vary the degree of the curve, so this saturation condition still holds. So sometimes I think in the physics literature, this situation when you can have like multiple solutions to this equation, some of the degrees omega alpha. So in kind of Fano case, you typically have like unique solution for beta. And okay, so let's forget about G part. So for fixed G, you will have like unique solution for beta, given some omega alpha. However, in this Calabi-Yau case, if you fix G and fix omega alphas, you may have multiple solutions for beta because first Chern class vanish. So curves of different degree can contribute to the same Gromov-Witten value. Yeah, so and that is what is called resonance case. So it's kind of some special situation when we lose beta dependence of our answer. So similarly, we can look at genus dependence of that formula. So for genus dependence, okay, so just for the sake of completeness, the kind of the final situation is C1 of X is negative. So in this situation, the kind of dimension decreases by decrease. So it means that that kind of, if we fix some omega alpha and try to increase the degree, so then we should like remove some of the omega alphas because dimension of moduli space decreases, and at some point we will just have like no omega alphas to insert, and virtual dimension would literally go negative. So it means that there is no kind of interest in curve counting. So that's why this situation is kind of not very interested from curve counting perspective, and only kind of Fano case and Calabi-Yau case are interested. And in our course, we will focus on this case. So we will not talk about resonance case of Calabi-Yau, but we will talk about Fano variety. So we can do a similar analysis so we did this analysis for degree dependence, but we can repeat this analysis for genus dependence. So genus dependence is much easier. So what we see that we have three cases. So complex dimension of X is less than 3, complex dimension of X equal to 3, and complex dimension of X is more than 3. So what happens in each case? So complex dimension of X is less than 3, so this number is negative. So it's negative number multiplied by 1 minus G means that the kind of dimension of a moduli space is something plus some positive number times G. So the dimension of a moduli space would grow with genus. So the curves with higher and higher genus will have more and more moduli, and therefore we have like a huge tower of interesting numerative problems. We increase the genus of the curve, and we add more and more observables. So similarly, here when dimension is 3, this kind of resonance case. So for dimension independent of G. So roughly it means that the kind of is the same observables omega alpha, but with the same cycles, we can have curves of a different genus that kind of satisfy the matching of degree of the forms and dimension of the model space. And here I want to notice that our kind of original example, not our original example of a mirror pairs and all this mirror symmetry business, it started with three-dimensional Calabi-Yau, which is a very special double resonant case. So its dimension is 3, so the number of the model space dimension is genus independent, and the first kind of Chern class vanishes. So and it's beta independent. So therefore, when I mentioned about curve counting by Candelas on a quintic, I never kind of mentioned what degree of the curve. No, sorry, I mentioned. Okay, I never mentioned genus of the curve, so there was some genus independent, but still there was some distinction of the curves of different degree. But still, like in that situation, I kind of never mentioned about passing through some cycles whose number depends on d. Like on P2, for a curve of given degree and given genus, we need like 3d minus 1 plus g points to kind of make this counting finite. So there was like dependence on the number of these observables that depend on both d and g. While in quintic case, we can still distinguish curves of a different degree and different genus, but we don't need to vary kind of observables. We can just kind of, I think, let observables empty and count the degree and count the number of curves, because in double resonant case you can just set n to 0. So this blue square is 0, red square is 0. So everything is 0. So moduli space is 0 dimensional. So therefore it's some kind of finite collection of points, and you can just count how many points you have. And once again, when dimension of x is bigger than 3, so then the dimension of a moduli space decreases with genus, and kind of there is no sort of interest in high genus Gromov-Fit invariance, because at some point you just get like negative dimension, and no cycle distortion would help. So once again, our course will. So in our course we kind of mostly will be. So in our course, we will be focusing, instead of looking at different genus, we will be mostly focusing on the curve of the fixed genus. So maybe at the very end of the course, we will briefly touch this case, like what happens to high genus curves in kind of when complex dimension of x is less than 3. So, but mostly we will focus on even simpler situation. Genus is 0, so we will completely fix this blue term, and we will have C1 positive and kind of very big. Okay, so that was kind of some observations based on integral formula for Gromov-Fit invariance. And in last question, just kind of briefly outlined how consecutive minus got their result, and we will talk about tropicalization of that result and the mirror dual, explicit mirror dual on the next lecture, or maybe I will. Okay, so there is also one kind of important special case when degree just equal to 0. So maps of degree 0 literally just map our sigma g n to a point inside X. So therefore, kind of moduli space of such maps is just kind of moduli space of kind of complex structure on the Riemann surface, and the moduli space of marked points, Cartesian product with X. So if you further specialize to the case when genus of the curve is 0 and n is 3, So we have sphere with 3 marked points. And famously, the kind of M03 is just a single point. So due to SL2C action that I also mentioned at the beginning, so this moduli space, it has like dimension 0, because by SL2C transformation you can bring any 3 points to some fixed points, say 0, 1, and infinity. So therefore moduli space is just point. And that gives us a very simple formula for Gromov-Witten invariant, when we just have like 3 cycles, have genus 0, 3 marked points. We have genus 0 and degree 0. I think I labeled them as G vector. So in this situation, the moduli space is just X, and the evaluation map became just trivial map. What we have here, gamma 1, gamma 2, gamma 3. So it's just integral of X of product of 3 forms. So in kind of geometric side, if these things, if we kind of substitute instead of gamma alpha on current duals for a cycle C alpha, so then this number will be kind of triple intersection. Okay, so we are in kind of complex geometry case, so we don't need to worry about extra signs. So we just count in triple intersection points for C1, C2, and C3. So pictorially, it looks the following. So we have C1, C2, and C3. And C3, and they can have, say, multiple intersection, say something like this. So and what we count here, we count like triple intersection points. So therefore, Gromov-Witten invariants, they kind of generalization of triple intersection points. So what happens if we say increase, like keep G 0 and increase beta? So there is also nice geometric interpretation for this situation, which is intersection of 3 cycles, but not over a point, but over genus 0 curve with 3 marked points. So the picture looks like this. So these 3 cycles, they do not intersect between themselves, but they kind of intersect this image of a white curve. So therefore, this Gromov-Witten with kind of 3 orthogonals, 3 points. Gamma 3, X, then 0 degree beta, this kind of intersection. There are delta functions of Yeltsin, intersection of C1, C3, over image of degree beta map. So we have genus 0 curve, which is some kind of P1. So we map it into X by degree beta map. And then Gromov-Witten invariant just kind of counts this kind of modified intersection where we kind of inflated intersection points into whole curves. And similarly, kind of if you have invariants for different betas, then the taken beta to 0 is just shrinking our image of our curve to a point and counting intersection. So when we look at this intersection given by this integral, it has very nice property that we can first. So this integral only depends on cohomology classes because X has no boundary. So changing gamma by d of something wouldn't change the integral. So therefore we can use the product in cohomology to express product of gamma alpha and gamma beta. Once again, as a sum cohomology class. So that is product in H of X. And then therefore we can express triple intersection numbers in terms of this product and some Poincare pairing on cohomology. So this n gamma 1 gamma 2 is just Poincare pairing where you multiply forms and integrate them away. So therefore this Gromov-Fit invariants of kind of genus 0 degree 0 they would be expressed through some structure constants of product and cohomology. So product and cohomology is an associative product. So yeah, so this multiplication in cohomology is associative. So hence the phi alpha beta rho satisfy quadratic relations. So it's roughly like alpha beta sigma is sigma delta mu if I first multiply beta gamma get sigma and then multiply alpha and sigma and get mu. So there are quadratic relations on this structure constant that describe multiplication in cohomology ring in some basis. So the structure constant satisfy quadratic relations and kind of by this relation of this structure constants to Gromov-Fit invariants. So this Gromov-Fit invariants also satisfy quadratic relation. So that was kind of simple part. The interesting part is that if we look at generalization of these things, so if we generalize this thing to allow for arbitrary beta, but we combine different contributions with different beta with some generated function, some kind of Q1, beta 1, Qn, beta n. So beta is some n-dimensional vector where n is dimensionless with Q of x. So here we have over the positive part of H2 of x. So we get some kind of structure constants. But now that they are functions of Q. And evaluated at Q equals 0, they give us structure constants, okay, modulo this Poincare duality, structure constants of multiplication on cohomology. So the Q dependence of a structure constants surprisingly also gives us a structure constant in a sense that they still satisfy quadratic relation, like associativity induced quadratic relation, as this kind of functions of Q. And these structure constants, they are structure constant of some associative ring, and in this ring.
But now the structure constant contains 3 indexes.
Yeah, but as I say, like I can use this Poincare pairing to kind of raise and lower index, and this eta, it doesn't acquire any Q dependence. So this eta is just the same for kind of ordinary cohomology and for this module. And the kind of so this multiplication is a multiplication on this linear space of cohomologies, and H star of x endowed with multiplication with the structure constant They are often called quantum cohomology rings. So I don't call it quantum cohomology ring. And Q is this deformation parameter that deforms ordinary multiplication to a quantum multiplication. And the geometric interpretation of quantum multiplication is that instead of counting like triple intersections, we count triple intersections over curves of different degrees and sum them with some weights. And it turns out that using this kind of property that the structure constants computed from Gromov-Witten invariant satisfy this quadratic relation, we can derive this Kontsevich-Manin recursion formula. So,
sir, I think maybe this formula need associative for the big quantum product because there are more than 3 quantum insertion.
Okay. So, yes, you. Okay, so there is kind of the story is the following. So formally, yes, you need more insertions, but in a P2 case, insertions of additional points can be kind of related to just deforming Q, like Q deforming to the key, and then kind of key expansion would give me a kind of Gromov-Witten invariance with more points, but essentially this key dependence can be restored from Q dependence. So therefore, secretly, quantum cohomology in P2 are just enough to get Kontsevich-Manin recursion. But we will kind of talk in more details about that formula and some kind of object that underlines it, like WDV equation. I think maybe on the next section, I think it's important subject, so we will move our schedule a little bit from syllabus, maybe by half of the lecture to talk in details about WDV equation and kind of in details how to kind of fill the gap between associativity of quantum cohomology and Kontsevich-Manin recursion. But I really need to stop because I'm already over time. I apologize for going over time. So I will post like lecture notes for today's lecture maybe in 1 or 2 days, and hopefully I will get like video from our IT team also within a couple of days, and I will also post a link to every chat. So and the first homework will be after second lecture. So thank you for coming.